Okay, so we're going to start with Laplace and Z transform. I will tell you that Laplace and Z transform is going to be very easy, very easy when compared to the Fourier series and Fourier transform that we have learned. But having said that, the core part of signals actually belongs to Fourier series and Fourier transform only. Okay, once you understand that this particular part of Laplace Z, or it may be discrete time Fourier analysis, is actually the concept which is based on Fourier series and Fourier transform only. Okay, but having said that, this part of Laplace and Z is very simple and it is very scoring. Okay, but the core part of signals is going to remain with the Fourier series and Fourier transform. So therefore, I am saying again and again that please focus on these two parts. Don't leave it. Okay, because once you leave this particular part, considering it is difficult and you are not giving time, you will never get confidence on signals and systems. So it's my humble request to all of you that please focus on this particular topic of Fourier series and Fourier transform, because once you do that, you know before that it is simple introduction to signals and systems, where we have shown shifting, scaling, reversal, energy signals, power signals, and different types of signals that you have learned. System properties we have learned. That's it. LTI systems we have learned only about convolution. That is very simple part. After Fourier series, Fourier transform, now you are going to see about Laplace transform, Z transform. Again, you will enjoy this particular class like anything, because it's very simple and very enjoyable. And after that also, discrete Fourier analysis is purely based upon the Fourier series and Fourier transform that you have learned. Okay, so to get the confidence on this particular subject of signals and systems, you have to focus on Fourier series and Fourier transform. The advantage we have here in this particular case is the content in Fourier series and Fourier transform. You can blindly believe me, it's very narrow, and whatever questions are going to be framed are only going to be framed from the concepts that we have discussed in the class. Okay, so that is a very big advantage you're going to have. What all you have to do is that you have to open your notes, you have to revise it again and again till you are getting the comfort on that particular topic. If you are having any doubt, of course you can ask the doubts wherever it is required. Okay, so having said that, we can start discussing about the concept of Laplace and Z transform. So before going to this, we have to understand why are we learning this particular topic of Laplace and Z transform. Let me tell you, Laplace and Z are nothing but like twins. Okay, if you learn Laplace transform, you are actually learning Z transform. There is nothing which is present in Z transform which is unique. Only the representation is unique, but the purpose why we are using Laplace is same as the purpose why we are using Z. The only difference is that Laplace we will be using in continuous time domain, and Z we are going to use in the discrete time domain. But the function of both of them is exactly the same thing. Okay, so Laplace and Z transform. Why are we learning this? I think I told you that that the Fourier, he was a scientist, he has actually worked under Laplace. Okay, and we know that, so whenever a student does or a junior does a mistake, a senior can understand or a mentor can understand and he can correct the mistake. So it is not a mistake in the Fourier's case, but there are some limitations which happened in the case of Fourier series and Fourier transform, for which Laplace has tried to slightly manipulate the tools of Fourier series and Fourier transform to have a tool of Laplace to overcome the limitation. Now what is that limitation? The limitation of the Fourier series and Fourier transform is that they cannot be generally applicable for unbounded signals or unstable systems. Okay, they cannot be applicable for unbounded signals or unstable systems. So in both the cases, your Fourier series and Fourier transform, or I can say the Fourier analysis, is going to fail. Okay, your Fourier tool is going to fail whenever it looks at the unbounded signals or unstable systems. In those cases, we cannot apply the concept of Fourier series and Fourier transform. In many of the cases, we have proved that the ramp function or exponential function which is growing, we have seen that the Fourier transform or Fourier series is not at all applicable. So that is the very big limitation that is going to be overcome by the concept of Laplace. There are many more advantages. That is the reason why you don't only see Laplace in the case of signals. You will see Laplace even in mathematics, you see Laplace even in controls, you also see it in networks. So many places you learn about Laplace. The purpose why Laplace is famous is because it has overcome all the limitations that we are having in the case of Fourier series and Fourier transform, so that we can transform a signal from the time domain to the frequency domain. Okay, transform the signal from time domain to the frequency domain. One more advantage that the Laplace carries is that if you are having any particular system, okay, and you want to model a system, one of the way of modeling the system is using the Laplace representation. A Laplace representation. Number 3 is that whenever you are writing a particular system in terms of a differential equation. In mathematics, we have learned that any particular system can be represented in terms of a differential equation. And whenever you are looking for the solution of a differential equation, sometimes it is very complicated to solve the problem of a differential equation. So therefore, if you are using the Laplace domain, it becomes easier to solve the solution for the differential equation. Okay, so to represent your system on a whole, you can use this particular Laplace domain. To represent the system, you can use your Laplace domain. It will also help us in solving the particular differential equation, which is represented by the system. Okay, like that there are many more advantages of using the Laplace. Okay, anyway, we are going to get into this particular topic of Laplace. So the standout advantage of using the Laplace is that it provides the frequency domain. For unbounded signals and unstable systems. So it is a very good tool to manage this signal which is unbounded and a system which is unstable. Okay, so it provides the frequency domain for the unbounded signals and also the unstable systems. Now, how this particular thing is done by Laplace? Let us try to understand this particular aspect. Let us take an example where the Fourier transform fails. So if I consider a signal which is something like e power 3t u of t. So basically, because of the presence of u of t, the signal will only be present for t greater than 0. So it will be starting from 1 and it is going to be exponentially raising function. Can we apply the Fourier transform on the signal? Is it possible for me to apply the Fourier transform on the signal? Yes or no? It is not possible whatsoever to apply the Fourier transform on this particular signal because of the fact that it is an unbounded signal not satisfying the existence criteria. So therefore, I cannot apply the concept of Fourier transform on this. Now, what Laplace has done here in this particular case is that the signal f of t, let me consider this particular signal as f of t. This particular signal f of t is now multiplied with that of a damping function, and the damping function is e power minus sigma t. So the signal f of t that I have considered here is now multiplied with a damping function called as e power minus sigma t. Now what he has done is that it has damped and he has changed the values of sigma. He has tried to vary the values of sigma. So what are the possible values of sigma he has taken? He has started from sigma equal to 0, let us say. In fact, we can go for the sigma less than 0 also. Let me start with sigma equal to 0. So this particular function can be written as e power 3t u of t. So e power 3t u of t multiplied with e power minus sigma t. This becomes e power 3 minus sigma t u of t. It is going to become e power 3 minus sigma t u of t. Now I will vary the different values of sigma. So if I consider the value of sigma to be equal to 0, it becomes e power 3t u of t. Okay? If I put the value of sigma equal to 0, it's e power 3t u of t. Can I take the value of sigma equal to 1? If I take sigma equal to 1, then it is going to become e power 2t. Sigma is equal to 2, it's e power t. Sigma equal to 3, it becomes u of t directly. It becomes u of t. If I take sigma equal to 4, it becomes now a decaying function. sigma equal to 5, sigma equal to 6, sigma equal to 7, sigma equal to 8, and so on. So after multiplying with the of e power sigma t, and I varied the different values of sigma, and I again wanted to see after multiplying in which aspects I can apply the Fourier transform. In which of the following cases can I apply the Fourier transform? Obviously, we cannot apply the Fourier transform for sigma equal to 0, can I? Can I apply the Fourier transform for sigma equal to 0? Not possible. Can I apply can I apply for sigma equal to 1? Not possible. Can I apply for sigma equal to 2? Not possible. Can I apply for sigma equal to 3? Can I apply for sigma equal to 3? Let me tell you, even this is not possible. Even this is not possible. Why? Is because of the fact that the Fourier transform is applicable when the tool of Fourier transform is applicable when it is absolutely integrable. When it is absolutely integrable, and we know that for sigma is equal to 0, sigma equal to 3, we are having a step function, and even in the case of step function, it is not absolutely integrable. That is why we did not have a direct Fourier transform in the case of a u of t function. We had to approach in an indirect way because of the fact that it is not satisfying the criteria of the existence. It is not satisfying the criteria of the existence. So, any value of sigma greater than 3, any value of sigma greater than 3 is going to make this function a decaying function. Is going to make this function a decaying function. Not only sigma equal to 4, any value of sigma which is greater than 3 is now going to make this function a decaying function. So whenever you are having a decaying function, yes, I can apply the Fourier transform in this case. Yes, I can apply the Fourier transform in this case. So what the Laplace has done here, he tried to multiply the same function f of t for which the Fourier transform is not possible. Now he tried to multiply and for different values of sigma, and he has ensured that there is a region of sigma for which we can apply the transformation for this particular signal. There will be a region of this particular sigma for which I can apply the Fourier transform. So Fourier transform is still applicable, but it is now a function of sigma. But now it is a function of sigma. So in this particular case, what I am checking here before applying the Fourier transform is that whether the existence condition is satisfied or not. What is the existence condition? Mod of f of t e power minus sigma t, right? Because of the fact that I have multiplied the signal with e power minus sigma t, so what I am doing here, I am taking the mod of f of t power minus sigma t and I am checking whether it is less than infinity or not, whether it is absolutely integrable or not. Now when this condition is satisfied, when it is going to be satisfied, for any value of sigma which is greater than 3, this condition is now going to be satisfied. So any of the case where it is satisfied, I can go ahead and apply the transformation. So what I can do in this particular case here is that for the cases where above condition is satisfied, I can apply Fourier transform. So the Fourier transform can be applied. Fourier transform can be applied. So I will apply the Fourier transform for f of t e power minus sigma t. I will apply Fourier transform for f of t e power minus sigma t. Right. So what I will have here, integral minus infinity to infinity f of t e power minus sigma t. This is the function for which I am applying the Fourier transform, e power minus j omega t dt. E power minus j omega t dt. So now f of t e power minus taken as common sigma plus j omega multiplied by t dt, integral changing from minus infinity to infinity. So I can consider that sigma plus j omega is equal to s. integral minus infinity to infinity f of t power minus st. So this is what I can write it as f of s. This is what I can write it as f of s. So we call this f of s because once we solve this particular function, we will have it as a function of s. Once you solve it, you will have it as a function of s. This is what we call as the Laplace transform of f of t. This is what we call as the Laplace transform of f of t. So what is the relation between Laplace transform and Fourier transform? Is simply the Fourier transform of f of t multiplied by the damping factor. The Fourier transform of f of t multiplied by the damping factor is nothing but the Laplace transform of the function f of t. Okay, so whenever you are considering a Laplace transform, you have to multiply your function f of t with the damping factor e power minus sigma t. That is what you are going to give you the Laplace transform f of s. So I can say that f of t is now going to have the Laplace transform pair as f of s. So f of s is equal to integral minus infinity to infinity f of t e power minus st dt. Okay, so this is the formula for the Laplace transform. Very, very important formula. Please note it down. Please write down existence condition of Laplace transform. 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 So what is the existence condition? What is the existence condition? Integral minus infinity to infinity mod of f of t e power minus sigma t dt is less than infinity. So this is the existence condition for the Laplace transform, because you have multiplied with e power minus sigma t, that will be the part of it. Now this will be the existence condition for Laplace transform. The existence condition of the Laplace transform is given by integral minus infinity to infinity mod of f of t power minus sigma t dt, which is less than infinity. So this particular part has to be absolutely integrable. This particular part has to be absolutely integrable. Please write down region of convergence. Region of convergence of Laplace transform. 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 Please write down the values of sigma. The values of sigma for which the existence condition of Laplace transform, the values of sigma for which the existence condition of Laplace transform is satisfied. The values of sigma for which the existence condition of Laplace transform is satisfied is known as region of convergence of Laplace transform. Is known as region of convergence of Laplace transform. Is known as region of convergence of Laplace transform. So what ROC means here? We call it as ROC. ROC simply means that particular values of sigma for which the existence condition is satisfied. For which the existence condition is satisfied. Yes, please write down the values of sigma for which the existence condition of Laplace transform is satisfied. The values of sigma for which the existence condition of Laplace transform is satisfied is what we call as the ROC. Is what we call as the region of convergence. So in the previous example that we have taken, e power 3t u of t. The previous example that we have taken, which is e power 3t u of t. Can you please tell me the values of sigma for which the existence condition is satisfied? What are the values of sigma for which the existence condition is satisfied? The existence condition has been satisfied for sigma greater than 3, yes or no? It has been satisfied for sigma greater than 3. And sigma is what? Sigma is the real part of S, right? when we have written S, when we have defined S, S is nothing but sigma plus j omega. S is nothing but sigma plus j omega. So real part of S is nothing but sigma. Real part of S is nothing but sigma. So when we are drawing the S domain, we will be having sigma as a real component and omega as an imaginary component, because S is nothing but sigma plus j omega, as we have defined earlier. S is nothing but sigma plus j omega. Sigma is the real component of it and omega is the imaginary component of S. Now when we are drawing the ROC, we can have a graphical representation of ROC. For the previous case itself, I can have a graphical representation of ROC, that let us say this line is sigma equal to 3. Let us say this particular line is sigma equal to 3. Any region which exceeds 3, any part which exceeds 3 will become the ROC of this particular function. Which just indicates that the region in which the Laplace transform is applicable. It indicates the region in which the Laplace transform is applicable. Okay? Because the existence condition is satisfied. Existence condition satisfaction becomes a very important criteria for having a Laplace transform. If the existence condition is not satisfied, then we cannot apply the Laplace transform. So ROC just gives you the graphical representation where you can apply the Laplace transform. It just gives you the graphical representation where you can apply the Laplace transform. So this is what we call as ROC. So when we are drawing the graphical representation, we are having a sigma as the real part. Sigma is the real part which becomes the x-axis, and j omega, which is an imaginary part, is now going to become the y-axis. So purely we call it as a S domain. We call this particular as a S domain. So any particular part which is greater than that of sigma equal to 3 is going to be the part of the region of convergence. Please note it down. Find the ROC and Laplace transform of del of t, u of t, u of minus t. We have to find the ROC and the Laplace transform for del of t, u of t and u of minus t. So first let us start with the top del of t. Right. So when we start with the top del of t, the very first thing that we have to do is whether it is satisfying the existence criteria or not. Mod of del of t e power minus sigma t. Whether this is less than infinity or not. Because this particular function is a positive function, del of t is also a positive function, e power minus sigma t is also a positive function. There is no requirement of keeping a mod. And we know that del of t is multiplied by some function of time. Yes or no? Del of t is multiplied by some function of time, correct? So when you are multiplying your del of t with a function of time, you are having something like f of t multiplied by del of t. Can you please tell me what it is? What is this? So f of t multiplied by del of t, what is the result going to be equal to? F of t multiplied by del of t. It will be f of 0 multiplied by del of t. Or in a way I can put the value of t equal to, I can put the value of t equal to 0 here. So if I put t equal to 0, then integral minus infinity del of t dt is equal to the top 1. Integral minus infinity del of t dt is equal to the top 1. So the existence condition is satisfied. Now can you please tell me, does the existence condition depend on the value of sigma? In this case, does the existence condition depend on the value of sigma? Yes or no? The existence condition is not at all depending on the value of sigma, right? It's not at all depending on the value of sigma. So it means that I can have my ROC from any value of sigma which is from minus infinity to infinity. We can have our ROC from any value of sigma from minus infinity to infinity. So it simply means that it doesn't depend on the value of sigma. You can put any value of sigma that you require. So now if I wanted to have an ROC representation, the ROC representation will be the complete S-plane. So I'm not cancelling it out. I'm just saying that the ROC is going to be the complete S-plane. The ROC is going to be the complete S-plane. Right. So the Laplace transform of del of t. The Laplace transform of del of t. Let us find it. Is integral minus infinity to infinity. Integral minus infinity to infinity. Del of t multiplied by e power minus st dt. And again we can put the value of t is equal to 0 here because of the same reason that you are having a del of t multiplied by some function of time. So I can put t equal to 0 in this particular case. So I can have here area of del of t dt which is equal to that of 1. The area of del of t dt which is equal to that of 1. So what I can say here, that del of t will have the Laplace transform as 1. Del of t will have the Laplace transform as 1. Del of t will have the Laplace transform as 1. So the next function that we're going to consider here is u of t. The next function that we are going to consider here is u of t. So the first thing again is that we have to check the ROC. So we will take the existence condition and we will check whether it is less than infinity or not. Okay. So integral minus infinity to infinity mod of u of t power minus sigma t less than infinity. Of course dt is present here. Less than infinity. Right? So is mod required here? In this case, can you please tell me mod is required or not? Mod is not required because of the simple reason that u of t is a positive function, this is also a positive function. Now because you are having u of t, I can now extend from 0 to infinity only. Because we know u of t is something which is non-zero for positive value of t. So here u of t becomes 1 e power minus sigma t. Which we want to be less than infinity. Which we want to be less than infinity. Now please tell me one thing. If sigma is positive and sigma is negative, what is going to happen? Sigma is positive means, if sigma is positive, we are only talking about 0 to infinity. The function will be something like this. If sigma is negative, so what it becomes, for example, sigma is equal to minus 1, so minus minus becomes plus. You are having an exponentially growing function. Now, in this case, if you are trying to integrate from 0 to infinity, this is for sigma greater than 0 and this is for sigma less than 0. Okay. So, if I consider this particular part, then it's absolutely integrable. But if I consider this particular part, it is not absolutely integrable. So therefore what I can say is that only for the region of sigma greater than 0, we can have the value which is satisfying, which is going to be less than infinity. Okay, the area of it is going to be satisfying less than infinity only for the case of sigma greater than 0. Only for the case of sigma greater than 0. Please let me know once you have understood this or not. Okay, so we are having u of t here. So because of the presence of u of t here, limiting it from only from 0 to infinity, where the value of u of t is 1. Now we are taking the different values of sigma, sigma greater than 0, sigma less than 0. So in the case of sigma greater than 0, it will be a decaying function. In the case of sigma less than 0, it will be a growing function. Have you understood this particular part? Okay, so when you are considering the value of sigma greater than 0, then what will happen? Then the area of it is going to be a finite value. The area of it will be a finite value. Here the area is not a finite value, so therefore we cannot consider this particular region of sigma. Okay, so therefore my ROC in this particular case, for u of t, my ROC is going to be sigma greater than 0. So for ROC in this particular case is going to be sigma greater than 0. ROC in this particular case is going to be sigma greater than 0. Sigma greater than 0. Now let me find the Laplace transform. The Laplace transform of u of t is going to be integral minus infinity to infinity u of t e power minus st dt, correct? Now because of the presence of u of t, this will be reduced from 0 to infinity. The value of u of t is now going to become 1 e power minus st dt. Now if you solve it, this is going to become equal to 1 by s. If you solve it, it's going to be equal to the of 1 by s. Okay, in the same way you have to solve for u of minus t, you will get it as minus 1 by s, and the ROC is going to be just the opposite of it. ROC is going to be just the opposite of it. So if I want to represent the ROC in the case of u of t, the ROC in the case of u of t is going to be the positive part of it. So please, I request all of you to take this as the homework, that to find out that whether you are getting the same answer or not. This is for u of minus t. We are taking the amplitude of it for t greater than 0.